All right, everyone, I am here with Samory Kpotufe. Samory is an associate professor at Columbia University. Samory, welcome to the TWiML AI podcast.
Thank you. Thank you, Sam.
Let's get started by having you share a little bit about your background. You work in statistical machine learning. How'd you get there?
How did I get into statistical machine learning? Uh, somehow, I in fact started in math in undergrad in mathematics, and but then at some point I was doing mostly pure math in undergrad, and then at some point I wanted to do something that where I could see the applications of math, where I could see the impact of mathematics, um, and but I wasn't so sure, so I went off and worked for some time. Then at one point I was watching TV and saw robots on TV and got interested in how that was done. So I started applying for grad school, and yeah, and eventually I got into machine learning. I didn't know at the time that it was going to become a big field, and now it's a big field. So great, yeah.
That's awesome. And
Yeah.
tell us a little bit about your research interests. What do you focus on?
So very generally, I mean, I'm interested mostly in machine learning uh, itself. However, in statistical aspect of machine learning, and by statistical aspect, I mean questions such as how much resources are needed to achieve low error in classification, for instance.
Mhm.
And so, and by resources could be number of samples. It could also involve constraints on the problem. So maybe we cannot always have labeled samples. Maybe we have to return, maybe the classifier has to return a classification fast. And so there are all these potential constraints in real world applications that I'm interested in. And given those constraints, what is the best possible performance of classification procedures?
Mhm.
And so at a high level, that's my general interest. But I'm interested in being able to say mathematically, being able to give guarantees, being able to say mathematically, this is the nature of the problems we are looking at, and this is the nature of the best possible algorithms for these problems.
Okay. Yeah, I was going to mention that, we all care about the amount of data that's required.
Yeah.
But there's a little bit of a different, you approach that question from the perspective of a theoretician as opposed to a practitioner. I'm wondering if you can comment on kind of the relationship between theory and practice and the relationship for your work,
Yeah.
to practitioners.
So I'll say this. I feel like the theoreticians within machine learning uh, should mostly be inspired by practice. And so I try my best to be inspired by practice in the sense that I will look at practical problems and ask myself what would be the key questions that a practitioner might need answered and that the data might not reveal at once, right? And so I'll give you some examples of such questions, and can we use math to sort of understand these questions? And uh, so that's at a very high level. Given to give an exact example, if someone thinks, for instance, of clustering, right?
Hmm.
There are tons of different clustering procedures out there, tons of clustering algorithms out there, and the practitioner uh, has data in front of them, and they might ask, which one of these clustering algorithms should I use for my particular application, for my particular data? That's a question that is very hard to answer directly just from practice. Why? Because I'm taking clustering here because it's hard to even test anything. You don't have labeled data. It's hard to test the quality of your clustering if you don't have ground truth. So here you don't have ground truth. So the main thing you can rely on is modeling your problem and asking, under these assumptions I can make on my data, what is the best possible procedure? And so we try to answer those questions mathematically. And I hope that goes at it, answers it a bit for you. Yeah.
Hmm. Hmm. And maybe talk more concretely about the types of problems that you are trying to model. Do you think about them kind of very broadly at the level of clustering, classification, that kind of thing? Or do you make more granular assumptions about, I guess, both the problems and the data and the constraints and other things?
It depends on how far the particular question I'm interested in is, right. There are some questions where we are very much at a high level, where we are thinking about the basic task, such as classification, clustering, and such. And then there are problems that we understand quite well already. In those cases, I might start thinking about specific algorithms and how to distinguish between specific algorithms. Um, I hope I'm answering the question right. Maybe you want to make it a bit more precise.
Well,
Or should I make? Yeah,
I think the way to make it a bit more concrete is
yeah,
for us to talk about specific problems that you are interested in and
yeah,
some research, and kind of drill into detail there. You know, let's start with a recent paper or something that
yeah.
you're excited about.
Since we were talking about clustering, let me just give some concrete problems in clustering. Right.
Hmm.
So first, we all know at a high level how one might define clustering. The problem of clustering is I have data. I believe that the data comes from different groups, different subgroups. I don't have labels. So, however, I'm hoping that at least geometrically in some space, I should be able to discover that the data groups well into so many groups. Right.
Right.
So the issue that comes up right away is, what do we mean by the data groups well? We can say, for instance, that the data groups well in the sense that the data points belonging to the same group are closer to each other than to other data points. And that gives a sense of they cluster well. But the moment I say they are closer to each other, that means I'm making an assumption on the notion of distance, how far they should be from each other. And then the question comes up, what notion of distance is the right notion of distance here that I should be using? Right. So that all depends sort of on the downstream task. And so the theoretician might then start asking that question, what is the downstream task? And then what is the right notion of distance for this downstream task? Or we can go higher and say, how do we define clustering at all properly? Maybe this is not the right way to define clustering. Another way to define clustering is probably through densities. What I mean by that is, if I throw sand on the floor, right, I might say that, oh, the sand clustered into a few groups. And what do I mean by that? There is different density of sand in different parts of the space, the floor here, right? And so that gives me a different notion of clustering. Maybe what I'm trying to find in my data are regions of high density of points. Now that's a whole
You,
other. Sorry.
yeah, you would think that the two ways of looking at this, distance and density, they're measuring the same underlying phenomena. There's a
You
relationship there, but maybe one mathematical formulation or expression lends itself to the way you're trying to approach the problem more in
Yeah,
case of
yeah.
the other.
Exactly, exactly. Because that falls back also again into, what do I even mean by the distance
Right.
between points in the first formulation? In the first formulation, there are many different notions of distance that I might be looking at,
Yep.
right? And in this formulation here, the notion of a density is a bit more of a robust notion
Hmm.
in this other formulation. Uh, and then let's say that there is such a that I agree with that notion, that this is my notion. It's the regions of highest density,
Yeah.
right? Then there are tons of questions that come up. What level of density do I look at? If I look at a particular resolution, I might see particular clusters. If I zoom down, I might see even more clusters.
Hmm.
So there are questions that come up right away as to at what threshold am I cutting my notion of density?
Hmm.
And can we answer that automatically with an algorithm? Can an algorithm discover that automatically? And in what situations, depending on the downstream task, what notion of clustering should we be using? So the type of questions that come up there are, so first you define a notion of clustering. Next, you ask the question, under my notion of clustering, is it possible at all to discover the clusters? To what to what level can I discover the clusters? Meaning, what error do I expect if I have so many data points? So here I'm assuming there is a ground truth, of course. And what error do I expect with respect to the ground truth, depending on the number of data points that I have? And then the next question becomes that of what I call adaptivity. Adaptivity, or people might call it self-tuning and such. Every clustering procedure comes with all sort of tuning parameters. Here, an implicit tuning parameter that I threw in a second ago is, if I talk about densities, what density level,
Zoom
what
level, so to
resolution,
speak.
and that's sort of a tuning parameter.
Mm-hmm.
And so, are there algorithms that can look at the data by themselves and discover also the right tuning parameter? And we call that, at least in statistics, it's called adaptivity. And
Okay.
machine learning people tend to call that AutoML or self-tuning and such.
Mm-hmm.
And so, but those are the type of questions that me and other theoreticians ask. Are these possible at all? Is this possible? And if it is possible, what are the family of procedures that achieve these goals?
Mm-hmm. And so tying back to kind of this, the problem of the practitioner as the touchstone or inspiration, is the ultimate goal to be able to say, if your problem looks like this, or if your data looks like this, then do you want to use L1 norm, L2 norm, whatever, or this set of density metrics versus that set of density metrics?
Exactly. So that would be one goal.
Yeah.
That would be one way the theoretician can be useful to the practitioner,
Mm-hmm.
right? Is to be able to say that for these types of problems, this is the algorithms that seem to be, or these are the decisions, the practical decisions that seem to be most appropriate,
Yeah.
right? Uh, the big goal, I think, for any machine learner, whether theoretician or non-theoretician, is to come up with data algorithm that is sort of almost a black box and can decide on its own which situation it is in by just looking at the data. And that falls back into what I was calling adaptivity. It self-tunes. At the end, it has nearly no tuning parameter because all its internal tuning it does on its own and identifies the setting or the situation in which it is and adjusts itself. So it's a grand goal. We do know that very generally it's not possible, but we also do know that within certain under certain restrictions on the universe of problems, to say it is possible. And in fact, to some extent, humans do it, but it's because sort of our universal problem is restricted.
Mm-hmm.
Right.
And these kind of adaptive algorithms, is that something that well, you clearly, this is something that you're interested in
Mhm.
research. Are there specific examples of research that you've done that in this area?
Yeah. Uh, so for instance, I'll give a high level example. From here, during my PhD and maybe a little bit after my PhD, here are some of the problems I was looking at. I was looking at simple questions having to do with nearest neighbor methods. These are the most basic procedures out there, right?
Mm-hmm.
Nearest neighbor methods. We do know that nearest neighbor methods, when the dimension of the data is very high, do quite poorly in general,
Mm-hmm.
right? And you can show it mathematically that their convergence rate, whether you're in classification or regression, that their convergence rate uh, gets worse with dimension, right? And dramatically worse with dimension. In other words, how dramatic you need a sample size exponential in dimension in order to achieve decent convergence, right? At least in the worst case. So that's how we quantify that. So that's always been known, that dimension, and it's called the curse of dimension. That dimension is an issue. However, people then felt like, okay, maybe we can, if it so happens that the data is very high dimensional, but intrinsically is low dimensional. So examples of that, one example that I like to give is consider a robotic arm with sensors on the robotic arm. It has a lot of sensors, so it's generating a very high dimensional data set. However, the arm has few degrees of freedom. Yeah. And so we expect that that data lies on a lower dimensional surface in a very high dimensional space. And so what people then tried to do was come up with procedures called manifold learning procedures, which will try to discover that manifold and then re-represent the data in that sort of manifold space so that it's now lower dimensional, and then try to run these algorithms such as nearest neighbors in this lower dimensional space, where the hope is that it will perform much better here. So again, stepping back, we're starting with a very high dimensional problem, but we know that in a lot of machine learning applications, even though the data appears high dimensional, it's in fact often low dimensional. We just need to discover that lower dimension and then run the data, run the algorithm in that new space, in that lower dimensional space,
Mm-hmm.
right?
And
So
is manifold learning an example of dimensionality reduction, or is
yeah,
it a
exactly. It's an example.
parallel?
Yeah, it's an example of nonlinear dimensionality reduction.
Okay,
So
nonlinear.
now what you've done is you've increased the pipeline.
Mm-hmm.
Okay, so now you have your manifold learning procedure, which also has to make a decision, multiple internal decisions. What dimension is the manifold? Is it really a manifold? Is it really a smooth manifold, or
Yeah.
is it just a bunch of subspaces of different dimension? It has a lot of internal decisions to make. So in the end, your entire pipeline becomes this manifold learning plus the eventual classification, right? And you
Mm-hmm.
increase the pipeline. You've added in a lot of new tuning parameters, and so the question of adaptivity comes in. Is there just one algorithm that I can look at that automatically does as well as if I found the right manifold, the right dimension, everything?
Okay.
So that's where adaptivity comes in. What am I being adaptive to? I'm being adaptive to the structure of the data without knowing a priori the structure of the data. So one of my earlier work was trying to understand to what extent it is that existing procedures such as nearest neighbor already adapt to the structure of the data, to the intrinsic structure of the data, without needing manifold learning, without needing. There are other ways of re-representing data, reducing dimension in some ways. Dictionary learning is another one. So
Mm-hmm.
without needing dictionary learning applies in the cases of sparsity, where we believe that the data is high dimensional but it's very sparse.
Mm-hmm.
Uh, and so it so turns out that a lot of existing procedures are automatically adaptive to the structure of the data. And that came out mathematically by looking at the problem mathematically and then asking, oh, if we say now that my data that is very high dimensional lies very close to a low dimensional subspace, what convergence can we prove? And it so turned out that the convergence we could prove is then in terms of the lower dimension rather than in terms of the higher dimension.
Mm-hmm. So
Right.
so I can replay that, the these algorithms like nearest neighbor, that we could throw tons of different types of problems at, some high dimensional, um, will have problems in the general case with high dimensional data, but if the data happens to be data that has that's
This low
generated by,
dimensional structure,
yeah,
yeah,
exactly, then the performance of those yeah, it sounds like you're saying,
improve.
A, the performance of that algorithm is going to be more akin to what we'd expect if the dimension
Exactly.
if the data was low dimensionality. Um,
That's exactly what I'm saying. Yeah.
yep.
Here, all of a sudden, it turns out that these algorithms, and it's not just nearest neighbors. We are starting to understand that it's many other algorithms. It's particular classification trees. Uh, recently people understand that even things such as neural net are adaptive to intrinsic dimension in these ways. Things such as support vector machines are being understood as adaptive in these ways. But at that time, when I started working on these problems, it was a bit unclear what was adaptive in these ways. Uh, it so happened that I was, yeah, go ahead.
I think I have my question from
Hmm.
before. It's like, okay, is it two different things to say that the algorithms will perform better because the data has this inherent low
Structure.
dimensionality, this inherent structure,
Hmm.
versus the algorithms are adaptive? Is it um, is it some combination of the hyperparameters or something
Oh,
with
okay, okay. I see.
regards to
I see.
the
Yeah.
algorithms that makes them adaptive under a certain set of constraints of the data, or is um,
Okay, I see. I see. No, no. This is a very good question. Let me put it this way. Um, so I had two things in mind that would explain the question. So
okay,
first, I was talking about the entire pipeline.
okay,
If you were to do dimension reduction and all that, you see right away that one question that comes up right away there is what dimension should I reduce to,
okay,
which is a parameter of the problem,
yep,
right? What sort of low dimensional structure do I have, right? It's another hyperparameter of the problem.
hmm,
And I'm using the term adaptivity here loosely to say that I'm adapting to these various hyperparameters of the problem without knowing them a priori.
yep,
Exactly in the sense that you just explained, which is that if the data happens to be so structured, then we do automatically better without knowing that a priori. Now there is a nuance. What does it mean to do automatically better? Nearest neighbor methods are not just, in fact, are not just one algorithm. It's a family of algorithms.
hmm,
It's a family even in the simplest possible ways. So I can decide to run a nearest neighbor by saying I'm only going to use the nearest data point, or I'll use the k nearest data points, the
right,
two nearest or three or four. Those become parameters of the problem.
right,
So now there is another level of adaptivity, which is how do I choose those parameters automatically of the problem. So it so turns out that if I'm say in regression, depending on the loss that I'm using, if I'm say in regression, then regression is a hard enough problem that finding fine tuning to the best possible parameter is not as hard. Does that sort of make sense? Fine tuning to the best possible parameter is not as hard since the problem itself is hard and we cannot do so well anyway
okay.
in a non-parametric regression
The
problem.
complexity of the problem itself masks the complexity of
Exactly,
choosing the
mathematically,
parameters.
exactly,
Yeah.
exactly. And so here you can show that, in fact, you can just do cross validation on the number of neighbors,
Hmm.
and you'll get the best possible rate as if you knew what structure the data lied on.
Right. Right.
Okay. In classification, it's a bit more complicated.
Hmm.
Classification is a much easier problem than regression. And so it's a bit more complicated. Cross validation gets you half the way for hard classification problems. But for super easy classification problems, to get the best possible result, you might need more refined, quote unquote, adaptive procedures
Okay.
to choose now the parameters of your algorithm. And there are various ideas out there. And those are the various things I'm interested in. So,
Yeah. So I think the initial point that you made, that you're talking about the pipeline being adaptive as opposed to the algorithm, and even talking about the algorithm in this point
yeah,
is kind of
the reality of these things is that they are all the same. right?
Yeah, yeah.
An algorithm or the pipeline,
Right.
it's all the same because I can just make my algorithm more complicated and it becomes a whole internal pipeline. And so, yeah. And in fact, that's what I'll say this way, that for me, that's what neural networks are. It's just a whole pipeline of sub procedures.
Yeah.
Uh,
Yeah. 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 Interesting, interesting. And you're saying um you're saying also that kind of the process that we kind of typically use in practice to optimize these pipelines slash algorithms is the adaptive part, and we know that that's why.
Yeah, yeah, it's the adaptive part. So there are really multiple. I use the term adaptivity here, at least here, fairly loosely. In a research paper, I have to be very much more precise as to what I mean by adaptivity
Okay.
because yeah. But you're bringing exactly the type of questions why we need to make it more precise when we're saying adaptivity. There is the notion of adaptivity to various sub problems, families of problems, right? And then there is also the side problem of our algorithms themselves. Each you can view every parameter of your algorithm as trying to address one particular sub problem, and that's how they are tied. Does that sort of make sense? The
uh
parameters of
yeah,
our
I understand what
procedures
you're saying.
as
An example would be helpful, I think.
here. All I'm saying is that if I fix the parameter of my procedures,
Yeah.
right? If I just fix the parameters,
Yeah.
there is always one problem on which it's going to do well, right?
Right.
Okay, so in some sense, it's easy to think about it that way, that the parameters or the various configurations of my algorithm are addressing a subfamily of problems. And as I'm trying to be adaptive to a whole hierarchy of families of problems,
Hmm.
I need to also be tuning my algorithm,
Right.
finding the right parameter for the right problem. And right. And so those are those interactions that we are caring about, that we try to understand.
Got it.
Yeah.
So you're saying a broken clock is right twice a day. We just need to
Exactly.
find what
Yeah.
time we need to be
Yeah.
at.
And that's the perfect algorithm at that time. But what we're really caring about is an algorithm that works well across problems.
Right.
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 Yeah. And we
Um,
do know that in general, it's not possible. In general, in the following sense, you probably have heard such things as people talk about the no free
no
lunch
free lunch.
theorem. Yeah.
Hmm.
And so we know that in a general sense, it's not possible. But we do know that if we restrict the family of problems, it is possible to some extent. There are situations where adaptivity is not possible at all, and we might get into that when we talk about transfer learning, multitask learning, and all that. So, and where I hope, at least what I'm trying uh, to bring out, is the fact that adaptivity, in some ways, is what we are seeking in machine learning. We are seeking that black box procedure that looks at the data and just knows this is the type of data I'm dealing with. This is how I should self-configure to do as well as possible on this data.
Hmm. Um, so yeah, let's move on to transfer learning. What are you looking at in that area?
Yeah. So in that area, I feel like most theoretical questions are quite open, right?
Hmm.
So I don't know if I need to define transfer learning quickly here for, I mean, in fact, I should, because there is one thing. People use the term transfer learning and domain adaptation, all these terms uh, fairly loosely. And so when I'm using it, I need to be clear what I'm trying to refer to, right?
Okay.
Um,
I was going to say, in general, I would expect our listeners to be familiar with the term, but
Of
um,
course, yeah. I'm sure that the listeners are familiar with the
I
term, but
appreciate.
the key point for me here
Yeah.
is that when I use the term, I need to make clear this is what I'm trying to say, not some other thing that they
Right.
might have in mind, right? And so, transfer learning. What is transfer learning for me? Generally, we have I have data from a set of tasks. Sorry, I have data from, yeah, either a set of tasks or from a single task, and that data gave me information about a particular problem. Maybe it's a classification problem of some sort. However, the problem on which I like to do well is a different problem. So mathematically, we try to look at it as two different distributions. I drew data from a particular distribution, but that distribution is not representative of the eventual distribution that I would like,
Hmm.
right?
And you call
So
that a different problem, but that could also be the same problem with different data.
exactly, that could be the same problem with different data, and that maybe the data has shifted somehow.
Hmm.
And here is a simple case of the same problem, and in fact, that's where we're starting. Let's look at first the case where it's the same problem essentially, right?
Okay.
So I've given various talks on this on this so far, and I always start with the same motivating example. And the motivating example is Apple's Siri voice assistant, right? And if Apple people are listening to me, I hope they understand why I'm saying this. Apple Siri still doesn't understand me that well at all because I have an accent. And why? Because it was mostly trained on American English speakers at first, right? And uh, it's doing much better now, but one has to think about what they had to do. They had to acquire a lot more representative data. So you could view the original task as that, where they got data from a particular distribution, but it's a distribution of American accent, right? And then if you try to deploy it, let's say in Scotland, it's a different distribution, but it's the same problem. It's a different distribution of accent. You still have Americans there. You have some Scottish there. Here in the US, you have a few Scottish. There in Scotland, you have a lot more. So it has shifted, but it's the same problem. So at this point, there are various proposals out there to try and solve this problem faster. But what are the key issues? The key issues will be for the practitioner, how much more data should I acquire from, let me call it target task? How much more representative data should I acquire? So that's a question of resources, right? And then and here there is a cost, right? A financial cost, and we want to acquire as little as possible. So how little can I get by with? And that's really where the idea of transfer is coming in. What information can I transfer? And then there is the question of the how. How do I transfer such information? So what is the proper procedure once I have that additional data to transfer the information? Or do I need additional data at all? Right. So those are basic questions, right? And those questions, we want to try and understand them. We want to try and understand the principles behind them,
Hmm.
the principles behind transfer.
Yeah.
There,
And just to jump in, I love where this is going because I think, uh, and maybe this is more a practitioner than a theorist perspective, but I
mhm,
think, it's easy to kind of take a snapshot of, where transfer learning is today. Like you've got a neural network, you train it, you take,
mhm,
the lower layers, and then you kind of
yeah,
retrain on your top layers for your specific
for your
problem.
new data,
And
exactly.
that's
Yeah,
transfer learning. But I think you're
yeah.
suggesting that, yeah, actually, there's probably a lot of different things that one could think about doing to affect transfer, and maybe some are better than others.
Exactly. There are many more potential procedures there,
Yeah.
right? Here, for instance, you just described one, and another could be, and actually people do this. Maybe I'm going to take the new data and take my existing data, put it all together, pretend it's from the same distribution, and retrain everything.
Hmm.
Right. That's another potential procedure. And so there are many procedures out there, and but before, let's put it this way, let's even say that your favorite procedure is the one that you just described. I take a layer of a neural network. This is still presuming that I knew how to pick the target data. I knew which which amount of target data I should be using. Right. So there was a decision there also. So another basic question is there even a way for me to know a priori or to discover over time what amount of target data is required, is needed? If all of a sudden I acquire 1,000 data points and I'm not doing well, what does that tell me? Does that tell me that the I didn't acquire enough,
Or not the right.
or I'm not doing the right transfer.
Mm-hmm. Or not the right
So,
data.
or not the right data,
Yeah.
right?
Yeah. Just kind of
And
gets into
so,
like active learning and other
exactly. So
yeah.
there it
Right.
gets into active learning. It gets into a different form of active learning on the transfer. What are the limitations of that?
Mm-hmm.
It gets into uh, um, it gets into understanding what's the right notion of distance, or what's the, by distance here I really just mean information. What's the notion, the right notion of information to sort of quantify the information my original data already had about the target application, to be able to say that it doesn't have enough information, so I need that much more
Mm-hmm.
representative data.
I think what you're saying is if we had a way to know what it was about our initial training data that made it unique and special and most informative to the model that we've
Yeah,
trained, and what it was about the data that we need in order to have our model perform better on the transfer task, there may be a shortcut than what we're
exactly. Then we might start identifying the right data to pick
yeah, yeah,
and the right amount to pick.
yeah.
Right. And so
Mm,
some of my early theoretical work on this problem, I've only started on this problem a few years back. And some of the first questions there are that question.
mhm,
What is the right notion of information the source
mm,
has about the target?
mhm.
Right. And
How do you even begin to characterize that?
so so you cheat, right? That's the first thing you do. You go and you read a lot of papers because a lot of smart people have thought about the problem,
Mhm,
and you try to see, okay, what are the notions they've come up with, and what are the limitations of such notions,
mhm,
right? And then what's there still to be answered.
mhm,
And here, one of the things that I claim is that there are okay. This is the one thing that I'm still doing that every theoretician has done on this problem so far, which is model the problem as just probability distributions. I have data that I drew from a probability distribution. That's my source, and then there is another probability distribution which is my target. And then there are tons of notion of information that relates probability distributions, and also notions of distance between probability distributions. And then we can start there and start asking, do these notions of information or notion of distance, do they sort of capture the hardness of transfer? And I can say how hard transfer is if I had 1,000,000 data points from my source and just only 1,000 from my target, how hard would transfer be? And those are the places people have started. And so we started looking at those notions and then saying, okay, a lot of the various notions that people have looked at are notions that were developed in other areas, for in probability theory or in information theory and such, but were developed for other problems and not necessarily for the exact problems we are looking at: classification under a transfer setting. And in which case, we have to start looking at classification and then start asking what makes it easy to transfer a classifier from one distribution to another distribution, and what's entering that. So then we can ask, as we bring in the question, as we refine in the question, we can start seeing what's essential to the problem, right?
yeah.
So, for instance, if I'm using neural networks, I can ask the question, and I'll step away from neural networks even, and I'll just say I'm using a family of classifiers, right?
Mhm,
I'm using a family of classifiers, then I can step back and ask, okay, when is transfer easy? I can say transfer is easy if on my original data, my source has information about the target. If on for the particular family of classifiers I'm using, if whenever a classifier in my family does very well on the source, I expected to not be too far from the best classifier on the target. I expected not to do too bad on the target. That could be one simple notion.
mhm.
And that in itself start driving down a notion of distance between them, given my preferred set of classifiers.
And now we're talking about distance between the classifiers or distance between the data sets?
Distance between the data sets, or in
Okay.
fact, between the problems. because I'm viewing
Yeah.
the data set as being drawn from a distribution, which is now the problem that I have. And part of the problem is transferring using just my given family of algorithms. Maybe I'm using neural networks, maybe I'm using random forest, and that's my given family of algorithms. And that's the family of algorithms within which I would like to stay as a practitioner.
Hmm.
For my family of algorithms, the problem of transfer might be different, or the hardness of transfer might be different if I were to switch to another set of algorithms.
Okay.
And I hope that that one should be intuitive to people. If I'm using neural net, transfer on the neural net might not be the same as transfer on the classification trees.
Right. Right.
Right.
Right. Right.
And even though the data is the same.
Right.
Right.
So,
And so it's questions of that type that we try to answer, and then from there try to answer more refined questions. Once we start getting a sense of good notions, like meaning notions that are predictive of how hard transfer is, right? Then we can start asking other questions. Okay, now under these notions, we know how what's the best we could possibly do, and then we
mhm,
can start asking: are there algorithms that can attain this rate, that can attain this performance? And then, are there adaptive algorithms? Are there algorithms that can attain this performance without any knowledge about the underlying problem parameters?
mhm,
How much information about the problem parameters do I need to give an algorithm before it can do as best as possible for the problem?
mhm, mhm.
Right, and that's again where I fall back into adaptivity.
Yeah.
So,
Yeah. 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 Maybe just summarize this part. I think, a lot of what we're seeing in this conversation is, you hear often, machine learning works. We just don't know how or why it works. And
mhm.
I think you're illustrating in the context of transfer learning how a theoretician goes about trying to advance our understanding of how a particular thing works.
Exactly, exactly. And so, and I can tell you some of the simplest questions we are starting to address. Take the simplest or most naive heuristic in transfer. I take both data sets, throw them together, pretend it's the same, and rerun my training out and retrain my algorithms on this new data.
Hmm.
How well does this do?
Right.
Right. And so we can start answering those questions. Okay, it's nearly the best you can do in particular situations, and we can say what exact situations. It often has to do with how noisy your data is, and if it's not so noisy, and whether the pattern, your best classifier, is shared uh, between source and target. Is the problem the same? How close are the problems? And so under various situations, we can say, okay, this particular set of algorithms will do as well as possible. In other cases, the algorithms that do well will be, or are adaptive, will be closer to meta learning type procedures. And so we can start addressing those questions. But again, the whole thing for me is step back completely and start asking the most basic questions about the problem.
Yeah. 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 One
So,
more area I'd like to explore.
mhm.
You've also been doing some work in unsupervised learning. Can you talk a little bit about that?
Yeah, so it's mostly I mean, I've talked a bit about that so far with the clustering,
Yep.
although I didn't quite specifically talk about my work in clustering. Uh, and then lately, we've been looking at some applications in IoT,
Hmm.
in outlier detection, and such in IoT. So in clustering, mostly the type of questions I've looked at and I'm still looking at, there are two lines of questions. The first is what I alluded to earlier, which is, let's imagine that I define clustering as just notions of in terms of density levels, in terms of finding regions of high density in the data. To what extent can I do this? And can I do this also adaptively? Can I and there was a key question that we had, which was, um, there are tons of, in density based clustering itself, there are tons of heuristics. I will call them heuristics, and it's not a bad term. There are tons of heuristics that do extremely well in practice, and yet when you try to prove any guarantee about these heuristics, it's really hard. You cannot show that they, and however they do better than anything we can prove beautiful guarantees about. And so one of the questions there was, can we come up with a heuristic that competes with existing heuristics, and yet can guarantee the recovery of clusters if we define clusters as regions of high density of the data.
Okay.
Right. So it's that type of question there. Then lately I've been looking at um, uh, more. I mean, and it's coming up in more in the IoT domain, Internet of Things, and here the type of questions that are coming up I have to do with constraints on the clustering and alloy detection and all that. In IoT, we want to just monitor traffic, network traffic, and be able to quickly say when there is an anomaly in the network traffic.
Mm-hmm.
Right. And the anomaly could just be a new device was introduced into the into onto the network, into the house, or we are observing a new modality of the device, right? And these devices could be anything. It could be your uh, smart coffee maker, smart fridge. It could be a network. It could be a sensor in a city, etc.
And applications might be, anything from cybersecurity to performance management, et cetera.
Exactly. Yeah, etc. And and even detecting cybersecurity goes into it, right? Detecting simply that a new device was introduced and this device looks a lot like a camera.
Mm-hmm.
So somebody threw a camera onto my network,
Mm-hmm.
right? So something like that.
Yeah.
And
And from I guess you're getting to this, but your data sources like NetFlow, traffic
traffic,
flow.
and we are assuming that I can only observe the pattern of packets. I cannot read a packet, a network packet.
Yep.
All I know is that so many packets are being sent
Mm-hmm.
per second to these particular addresses and all that.
Yeah.
And so it's very unsupervised. I don't know it's an unsupervised problem. I don't have any labels. And however, this is where constraints come in. Huge constraints come into this right away. And the constraints are of the following form. Uh, we have to be able to run the detector, train and run the detector, let's say, on a router at home,
Mm-hmm.
on a very small device. We don't have a huge server to do this. So all of a sudden, a lot of outlier detectors out there. For instance, let's think about one class SVM. Uh, uh, it just don't run well in these settings.
Mm-hmm.
Why I'm taking one class SVM? One class SVM, like support vector machines in general, uh, require uh, a lot of computation. So require a lot of computation because they deal with these very large matrices that they have um to play with. And so right away, the question that comes up, questions of how do we reduce the data in some ways, right? Or how do we reduce this? If you're familiar with support vector machines, they work on a so-called gram matrix, which is essentially a representation of interactions between data points. Okay, but because the moment I talk about interactions between data points, if I have n data points, I'm talking about n squared operations already, right? And so we want to reduce this and reduce this quickly, and to be able to run on a nano computer on a Raspberry Pi or something like that, right? And so it's not only space savings, but it's also time savings. And so for me as a theoretician, the first question that comes up is, uh, first of all, can I maintain performance of a clustering after reducing data? And what type of data reduction is useful here? There are various things that people have tried. Nystrom, a method called Nystrom sketching method, all sort of subsampling method that reduce these data representations. And then the questions for me was, okay, can I modify this method and guarantee that, let's say, in the context of clustering or in the context of outlier detection, the performance is essentially maintained, and yet I've achieved my constraint
Mm-hmm.
on size. So it's questions of that type, and here it's very practical because I cannot just answer the question. I have to in fact implement it and get it working and eventually deploy it. And so
Okay. And presumably, is this work in progress, or have you come up with an
Oh,
algorithm
so
and
so so we have
implemented
a
it?
couple.
And
Yeah, we have a couple papers on it, and you probably heard of Johnson, Leader Strauss, dimension reduction, and random projection, things like that. So part of the work, the initial paper on this work was all theory, was trying to understand. Okay, there are all these problems out there, all these methods out there, sketching, Nystrom. Can we recast this method in different terms that we can understand better, right? So sketching doesn't look at right away like a random projection, and we're asking sketching, which is really just subsampling uh, of a matrix, can we view it as a random projection in a very high dimensional space, in an infinite dimensional space? Why infinite dimensional space? Because that's exactly where OCS VMs and all that work. They work in an infinite dimensional space. And I'm doing the sketching on a finite matrix. Can I view that somehow as a projection in an infinite dimensional space? Why do I want to view it that way? Because I do understand projections. We understand what projections do and what they maintain and all that. So that was the first step in the work. And then the next step has been, okay, now that we know how it works, we know for what type of clusters we preserve the clustering. And now, do we have that type of clusters in these IoT applications? It so turns out that we did a lot of data analysis, and okay, we do have that type of clusters often. And now we are implementing it, and we have a paper on archive trying to show that, okay, look at this running on a nano computer on the Raspberry Pi. It runs it runs 20, 30 times faster than the original OCS VM, but we have the same performance.
oh,
And
wow.
so, but it's understanding these type of things. And
Very cool. Very cool.
yeah,
Um, this may be a bit of a digression before we close out, but
no problem.
uh,
Yeah.
I was thinking earlier when we were talking about clustering and density and like zooming in and out, and kind of seeing the data at different granularities. It reminded me a little bit of like fractals and like fractal theory.
Hmm.
I don't just have has does that come up in
Yeah.
theory?
Yeah, it does come up a lot. So for instance, you might. So when I was talking about dimension earlier, and I was even when I was saying, okay, let's say data is very high dimensional, but it's very structured, right? Uh, there are tons of structures, tons of intrinsic structures out there. Manifold is just one, right? And manifold is just one such structure. And so, a first thing in that line of research was to try and understand um, what notion of intrinsic dimension can we use to capture all these low dimensional structures at once, rather than working on understanding each one of them separately? Is there a notion that captures them at once? And there are fractal notions of dimension that do capture these notions of intrinsic dimension at once. And then once you understand that, you can then ask the question, okay, let me now say that my data is low dimensional in the sense that its fractal dimension is small.
Mm-hmm.
How do nearest neighbors work?
Okay.
Right. So that's how we approach those problems. We first have to sort of step back again and say, okay, what is the essential quantity we need to work with here?
Mm-hmm.
And and fractals somehow have to do with representability of data or the information in something
Yeah.
in the data space. And so yeah. So a lot of notions we work with have this sort of recursive structure to them.
Awesome. Awesome. And one last thing, you're chairing a conference. That conference is happening now slash soon
Yeah,
slash
soon. Yeah.
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 Tell us about the conference.
So this is COLT, Conference on Learning Theory. And so COLT has been sort of the flagship conference for machine learning theory. I don't know how many years now, 20, 30 years, something like that. And so, yeah, so it's happening this year in what we all know are sort of unfortunate circumstances,
Mm-hmm.
the times we live in. And yeah, and this year, one of the things I'll say is that this year we have a really, really, really nice program. So let me put it this way. I feel that somehow at the same time we are in strange times and hard times for a lot of people, but people also tend to focus and solve hard problems around these sort of tough times. And I feel that reflected in somehow in the program we have. This year, a lot of beautiful problems were solved, and we were just awed at the type of results that to be presented next week at the conference. Yeah,
Awesome. Awesome.
yeah.
Well, we will include a link to the conference in the show notes, as well as the archive link to the network traffic representation paper. Samry, so great to catch up with you. Thanks so much for taking the time.
Yeah, thank you so much, Sam, for having me, and thanks for all the very interesting questions and the very pointed questions. So,
Awesome. Thank you.
yeah.